So my name is Mayank Jha. I am in University of Lorraine in Nancy, France, and I'm an associate professor here in the lab CRAN. Of course, most of the acknowledgements for the slides go to my PhD students, the former ones and the current ones, as well as my internal and external collaborators. We work with industries as well, including CNES, which is the Center of French National Center of Spatial Studies, Dassault Aviation, and recently with the startup Linkstrom. My talk is going to be theoretical in nature, and currently we are working with these approaches within the French national level research project called Self-Organizing Safe and Smart Technologies or Approaches for Fleet of Drones, where we are basically looking at developing such approaches for drones that are able to identify forest fires, navigate safely in complex environments, and contribute to firefighting missions, all whilst maintaining the safety of the system in such a way that the mission is guaranteed or the accomplishment of the mission is guaranteed. So, although we are working in such projects, my focus in this talk would be theoretical on the theoretical aspects, especially associated with safe reinforcement learning. I guess most of you know about control barrier functions and so on and so forth, but probably some of you may be new to reinforcement learning. So I would first give the background on reinforcement learning, especially from the automatic control point of view that leads to certain provable guarantees. And then my objective would be to talk about the end-to-end safe optimal regulation or end-to-end safe RL that we have developed recently, its extension to safe optimal tracking within the reinforcement learning paradigm. And if the time permits, I would very much like to talk about the input to state safety that we have we have developed very recently within the reinforcement learning framework. So what is reinforcement learning? Without very quickly, as you may know, reinforcement learning is all about learning the optimal policy or optimal sequence of actions that is learned by an agent based on its interaction with the environment. So typically there is an interaction between the agent and the environment. Agent sends the action that leads to a certain change, induces change of state within the environment. Based on the quality of change induced in the environment, a feedback signal is sent back to the agent. The agent takes into account the quality of feedback and typically tries to improve the action so that the next action is preferably better and at least not worse than the previous action. That's almost never the case during but that remains the objective. The objective is to learn for the agent to learn the optimal policy or optimal sequence of actions leading to the optimal change within the environment. The optimality is, of course, is defined with respect to the objective set up by the user in the model-based or model-free paradigm. Right. So now, why do I talk about this? So, for those of you from computer science background or computational intelligence society, would be using this language. But us in automatic control domain, we talk about adaptive dynamic programming. We talk about optimal adaptive controllers, and that typically involves similar topology, similar kind of strategy where the agent is typically the controller, the environment is typically the system, and the action is nothing but the control input. So here in adaptive dynamic programming or reinforcement learning framework, we have the controller sending controller input to the system that leads to a change. The change is then reflected in the reward, which is sent back to the controller. And the idea here, the objective here is to improve the controller in an iterative manner such that the controller is able to learn the optimal control policy or optimal sequence of control inputs, right? And of course, the optimality is relative, and it's with respect to the objective defined by the user in the model-based or model-free paradigm. Now, to illustrate the basic concepts, let me go. Let me not go much into the details. We all know about a nonlinear discrete time system such as this, affine in control, right? So I'll take a discrete time example, right, to illustrate some basic concepts. So here we consider uh, a system with standard assumptions on the smoothness in Lipschitz sense, on the existence of fixed point solution over a compact space, and so on and so forth. So let me not go into much in much details, but that's our system, and the objective is to learn a control law, an optimal control law, right, which can be and which is typically a state feedback control law, which needs to be optimal, and optimal with respect to the objective defined by the user. So in the objective function or the cost function, we typically consider the reward being the utility function, typically defined by the user. Now, as you can see, such a reward function can be defined in the sense of LQR, and if the system itself is linear, this leads to typically the learning of a LQR type of controller, right? But so we are in the nonlinear framework, so we have this kind of cost function. Let's consider the reward function as the LQR function here, right? So then once we have these concepts, we are able to typically define a value function with respect to with the control policy given. So a v pi here is the value function with respect to pi that quantifies, that models the importance of the control policy given the cost function. So that this value function is typically nothing but the cumulative reward over the infinite horizon. We can also set up the problem over a finite horizon, but hey, here we are in infinite horizon case, and value function is typically quantifying the importance carried by this control policy from state xk, right, at time k. So once we have a value function defined in this manner, we are able to write this value function in this manner, right? So we are able to decompose the value function at stage k into the present stage and everything that unrolls into the future, everything that remains thereafter. So the value function at xk consists of the present reward received and everything that exists thereafter. And such a function is also known as Bellman equation. It also serves as the nonlinear Lyapunov equation that can be used to assess the stability of systems and analyze the stability of systems under various scenarios. And I'm going to escape a lot of technical details here. And basically, then we are able to define the optimal cost, which is nothing but the minimum value over all possible control inputs. And that leads to the Bellman optimality equation, where the V star, if such a V star exists or optimal function exists, optimal value exists, it must be the same with respect to all the states. So V star with respect to xk is related to V star at xk plus 1 in this manner. This is basically Bellman's optimality equation. And then from V star, we are able to extract the pi star, which is the optimal control policy. So the whole objective, the goal of in reinforcement learning is to learn such a control policy which is optimal, pi star. But it is not easy to solve this equation, especially if in the presence of large state space. So if we have large dimensional or a large number of states, or even small number of states, but large states, large sized state space, there the computation becomes typically intractable. Why? Because you can see that this equation is backwards in time. Here, the V star at stage k depends on everything in the future. So if you know the future, you are able to back up and solve it. If you don't know the future, well, you need to learn it. So here, as you can see, there are two basic needs: learning the future, so making some bootstrapping kind of strategy, doing some guesswork, what lies in future, and correcting it, and so on and so forth. That leads to temporal difference, and so on and so forth. I'll not go into those details, but also, even if you know the future and in presence of large state space, such a computation can be quite challenging, and that's why we see the need of neural networks. I'm going to go to that very quickly. But remaining here, you can see that argmin basically taking the derivative leads to the expression of pi star, which you see here. Now, anal analytical closed form solutions of this problem, finding such solutions is hard, and that's why we take the help of iterative solutions. In particular, I talk about policy iteration. I'm gonna I'm going to forget value iteration. I'm going to talk about policy iteration, where we have three typical steps. The first step is initialization. We consider any stabilizing or admissible control policy that works as the initial control policy. If such a policy exists, we are then able to evaluate its importance with respect to the value. So with respect to the cost established by the cost function established by the user. So typically in the policy evaluation step, we consider such a policy and evaluate its importance or its value, right? This is done by simply computing the Bellman's equation using that policy. And once we have the policy evaluated, we use that policy to evaluate or to obtain a better control policy, right? So here, as you can see, we start with some control policy. We use that to evaluate the value function. We use the updated value function to obtain a better control policy. And this can be done sequentially. This can be done over and over till we converge to the optimality, or we obtain the optimal control policy, right? So over some taking into account some assumptions, in particular the compact space and existence of fixed point solution, we are able to show that the value functions are sequentially minimizing in nature or convergent in nature, and we converge essentially to the fixed point solution V star. And in this process, we obtain the pi star as well. So we are able to extract either pi star from V star, or in general, we are able to converge towards the existing fixed point solution under certain assumptions that I'm going to omit here. These are fairly established, right? So these are fairly well established in the literature. Now, as I said, to solve this equation in presence of large state space, it's not so easy, and the function v function itself, the value function itself, can be quite linear, can be highly nonlinear. So that's where the interest of using neural networks come into play, and so we used neural networks to approximate the value function, and we are able to solve basically the same problem using neural networks in an approximate manner. And there the idea is to use a neural network to approximate the value function. That becomes the critic neural network, for example. And we can do the same for the policy. So by using neural network as the approximator, we are able to approximate the control law as well. So policy iteration in general looks something like this, consists of initialization step, where we initialize the procedure using an admissible control law. Then we perform the policy evaluation using value functions that are approximated by neural networks, followed by policy improvement, right? As you can see, this expression looks familiar to you. We saw it here, right? Is the same expression here, but then instead of using exact value function here, we are using neural networks, right? And in the same manner for policy evaluation, instead of using V, we are using W, which are the neural network weights, right? So as you can see, it's conceptually, it's fairly standard and straightforward. And then once the optimality is achieved, with respect to some tolerance, well, we say that we have converged towards the optimal control policy under certain assumptions, of course. So that's the classic policy iteration, and that's almost 60, 70 years of work that I have just tried to summarize in 10 minutes. So pardon me for all the omissions. The literature is very well established in the domain of ADP, adaptive dynamic programming, and reinforcement learning based domain. It's very well established. If you have questions there, please feel free to contact me. My objective here was to give you the idea, the general idea, in a very quick and rapid manner. So that's conventional RL. That's the conventional reinforcement learning from the automatic control point of view, where the stability can be guaranteed, the optimality can be guaranteed, and typically these are the 2 points, these are the 2 properties that are focused upon. That's conventional RL. The safety is not really focused upon, is not investigated in the conventional paradigm. And that poses threat. Threat because reinforcement learning typically involves the exploration, that is the data collection phase, as well as exploitation, the learning phase. The data collection phase, as you may guess, is essential because we need data, system-based data, to train the neural network. Whichever neural network, or whatever be the neural network, right? The critic neural network that approximates value function needs data. The policy, the actor neural network that approximates the control policy needs data as well. And so typically that's the job. That's the job during exploration phase. And during data collection phase, the system may venture into dangerous regions, and that may violate, that may disrespect, that may lead to safety violations. And the same possibility exists during exploitation phase, where the controller is improving itself towards the optimality. So it becomes imperative to ensure safety during exploration phase as well as exploitation phase. And during exploration phase, it is essential as well to collect data which is rich, which is diverse, which is useful for the neural network training. And that's where the importance of SafeRL comes into play, where one should not see guaranteeing safety as a constraint optimization problem, because here we do not really treat safety as saturation. We need to ensure that the data collected is rich. The data that is being collected is as well diverse. We need to ensure that this control action that is taken at present stage K does not lead to safety violations in future. The environment may change, may be non-stationary. The safety definitions may change as well based on the change within the environment. So these are the complexities, these are the challenges, these are the problems that are being investigated in the SafeRL domain today. Also, of course, one should not forget the perturbation, the unmodeled effects, the uncertainty, stochasticity, and so on and so forth. So these are the challenges that are existing and that are being investigated in this area. What I'm going to focus upon, 2 aspects: safety during exploration and safety during exploitation. And typically, that typically means augmenting the policy iteration or the learning process with some safety guarantees, embedding within the policy iteration, within the learning process, some sort of safety-based certificates, and so on and so forth. So we are going to look at that. And the question that we ask really in these works that I'm going to talk about, we ask, is it possible to ensure safety during initialization, during exploration data collection phase, and during the learning phase? And that's what we call as end-to-end. That's that I will present shortly. And the key idea, since we are in control barrier function or based workshop, the key idea that we use is to use CBFs both as online filters during data collection, that is exploration phase, and also as an ingredient or as a function that we augment to the cost function during the learning process in order to ensure that the learning phase is safe as well. So how do we do that? So the key ideas are, first, during exploration phase, we are going to filter out the unsafe control inputs. So during exploration, we are typically exciting the system using, yeah. Is there a question? During the exploration phase, we are typically exciting the system, right? We are injecting the system with a control input which is noisy, using a probing noise, such as this, which is usually bounded. And the idea is to excite the system across the modes, right, in order to collect the data which is rich. So typically this exploration noise is rich in frequential elements, and with the objective to excite the system across the modes, right? And in this process, typically the system may venture into unsafe regions, and that leads to safety violations. So during the exploration phase, the idea is to augment this exploration process with CBF. So by using CBF, we are going to filter out the unsafe control inputs so that the exploration phase itself is safe. And during the learning phase, what we are going to do, we are going to use CBFs in a wise manner during the learning process in such a way that the control law which is learned is safe. So as you can see, so we have two steps at which the CBFs are not able to select this somehow. I'm gonna, yeah, this is much better. So we have CBFs coming into play here in order to guarantee exploration, and we have CBFs coming into play here in order to guarantee safe learning. How do we do that? Um, how do we do that? So in order to now get into some details, let me switch to continuous systems. Nothing changes. It's the same strategy. Of course, in terms of formalism, in terms of treatment, it becomes much more rigorous and different. We were in discrete time before, which was quite intuitive to illustrate the basic concepts. Here we are in continuous time. We have the system. You may recognize, I'll not go into details. We have the cost function. The value function is defined similarly. And typically the reward function is chosen as LQR, as you can see here. Well, not LQR, but QR, let's say. So something that is preferably convex, but semi-definite, positive, and so on and so forth. So we have the Bellman's equation and we have the control law, right? And that leads to the policy iteration, as you saw before. It's the same equation, but in continuous time. So we have the Bellman's equation here, and we have the control policy expression. And now, in order to perform this policy iteration, it's important to highlight the two strategies that exist: the on-policy strategy and the off-policy strategy. The on-policy is where we use a control law, a control policy, to excite the system, and we improve the same policy towards its optimality. We use the same policy to obtain the optimal control policy. So the same policy which is used to collect the data, excite the system, is improved towards its optimality. On the other hand, the off policy consists of a behavior policy, which is used typically to collect the data, excite the system, right? While there is another policy, target policy, which is improved towards its optimality in order to obtain the optimal control policy. We prefer off policy generally in SafeRL because, as you can guess, by wisely and intelligently choosing the behavior policy, one is able to ensure certain properties, in particular the safety. Most of the work that I'm going to talk about here will consider off policy. Uh-oh. There seems to be some There seems to be some problem. Can you see my screen?
Yes.
Sure.
We can still see your screen.
I can see my screen. Okay. So, yeah, that's okay. Right. And so let me skip all these details. You know, safe set definitions. We had some very nice, interesting talks in the morning. So all these, you know, these notations. So we are going to use a safe set. We are going to use HX, which is convex. So our focus is not on ensuring the HX is convex or not. We have HX, which is convex, and that leads to, so we do not have those feasibility issues during optimization. We have a safe set, boundary of the safe set, and typically the objective is to ensure the forward invariance of such a safe set in order to ensure the safety of the system. So all these details are fairly standard. I'm going to skip all of this. And you may also know about CLF and CBF QP safety filter. Let me skip this as well, where we typically combine, we use the CLF condition as a constraint, CBF condition as constraint in order to ensure that the filtered, well, the solution of this QP problem is a control input that guarantees the stabilizing nature of the control law as well as safety, right? And then, of course, the other ingredient, the other idea that we are going to use, as I said, is a reciprocal control barrier function. Now, by augmenting a reciprocal control barrier function here to the typical reward expression, we are going to learn the control inputs that push the system within the safe set. That's because the controller, during the learning phase, the controller learns, well, the controller typically tries to minimize this cumulative reward, right? And so when the system nears the safety boundary, this term barrier function explodes to infinity. And the controller tries to suppress the over cumulative reward and thus prioritizes safety over other terms or other criteria. While when the system is well within the safe set, the value of the barrier function is negligible or typically low. And there, the controller then works upon the performance and energy consumption, so on and so forth. So that idea is fairly straightforward. So that's how we would ensure safety during the learning. So let's once these ideas are clear, let's get into the end-to-end safe optimal regulation that we have proposed recently. I'll be skipping most of the technical details, and for that, please refer to these works that present various properties in a very rigorous manner. We consider this system which is continuous in Lipschitz sense, and here we are going to typically use a robust CLF CBF QP to ensure safe initialization as well as safe exploration. And we are going to use a barrier augmented value function to learn the safe optimal policy. And that leads to this kind of algorithm where we are able to initialize with any random policy. Thanks to robust QP, we are able to ensure safety during initialization. Thanks to robust QP CLF CBF, we are able to ensure safety during exploration. And thanks to the robust RCBF, reciprocal control barrier function, we are able to ensure safety during the learning itself, right? And that typically looks something like this. I talked about the idea. The idea remains the same. However, there are some technical details. It leads to a modification in the reward that leads to change in the value function. And so you will see in the journal, in the paper, we show that the modified value function also has certain properties. In particular, it's sequentially minimizing in nature or successively convergent. And we are able to obtain or tend towards the optimal solution in a successive manner. So these properties on the optimality, on the stability, and so on and so forth have been developed. And we are essentially able to ensure safety during the learning process. Why do we call it end-to-end? That's because we are able to ensure safety across the three important phases: the initialization, exploration, and the learning. So let me now, once learning aspect is clear, let me focus upon the exploration phase. So let's see what happens during exploration. During exploration, we are basically considering a probing noise here, and we model this probing noise as additive, as a matched additive uncertainty, or a matched perturbation, and which is bounded, of course. And instead of using CLF, we use the ISS CLF. As you all know, ISS CLF is fairly well established in the literature, and the CLF condition in for the system in presence of the perturbation or noise, right, or additive uncertainties. So essentially, we are able to write the input to state stable CLF expression for such systems, and that basically acts as the constraint that enforces stability or stabilizing nature of the solution. In the similar manner, we are able to develop the so-called robust RCBF condition using the reciprocal control barrier function in the presence of noise, in the presence of perturbation. We are able to develop such a condition that ensures safety in the presence of exploration noise. And by using these two conditions, we guarantee stability as well as safety of the system during the exploration process. So as you can see, the exploration process itself is formulated as a robust control problem. And so that's yeah. So that's the exploration process. And by applying such a robust CBF filter, we are able to ensure safety during exploration phase. The learning phase I talked about, so that leads to an end-to-end sort of safety where the initialization is safe, exploration is safe, and the learning is safe. Uh, Let me very quickly show some examples. So this is a car lane keeping problem. As you see here, in the first few seconds, we have exploration, right? Exploration is followed by exploitation or learning. As you can see, for this control policy, without any safety barrier, any safety guarantees here, the learning process is itself not safe. But the one with our strategy is safe. So that's about learning. What I would like to here show, what I would like you to focus upon is this exploration process, right, which is safe here. So typically we have exploration followed by exploitation. Now let's get into another example, which is jet engine surge and stall dynamics example. Here we used a fairly well established example that this model is fairly well established in the literature, and our focus is on X2 as the state whose safety must be guaranteed. So we use some initial states, initial policies, details are there, but what I want to really show you is the exploration noise that we use. As you can see, this exploration noise is fairly rich in frequential elements, right? And in fact, we also use some Gaussian elements here, which is truncated, so bounded. So we have the exploration noise, which is quite aggressive, at the same time bounded, right? So as you can see here, typical exploration can be highly conservative. So not a lot of data is being collected. By using such a noise, we risk violating the safety boundaries during exploration phase. That's typically the case. Now, with our strategy, we are able to guarantee safety during exploration phase while conserving the benefits of using such an exploration policy, because we are exploring, we are not so conservative here. Although this can be made better, that we'll see later, right? So the exploration phase is safe, and also the exploitation phase is safe using such a strategy. This leads to an end-to-end sort of um, guarantees. Now, let me talk about safe optimal tracking very quickly. So, the same strategy can be extended to the tracking problem, where, of course, the extension is not so straightforward in the sense that we have we have to ensure that a safe and admissible control policy exists. Only then such a problem can be posed. We haven't investigated the conditions that guarantee the existence of such a control policy a priori, but by using the very famous trick, we augment the system with states and the error. The error consists of is typically the difference between the reference and the state, right? And we are able to select one or few or all of the states that whose safety must be guaranteed, right? And what is important to also highlight is the fact that although the safety is imposed can may be imposed on one or all of the states, the tracking itself, the neural network, the tracking, the learning during this tracking problem, the neural network learns using the states as well as the error. That is, so augment using the augmented state during learning phase is important. And we use similar strategy but not the same barrier function. We have proposed the so-called normalized barrier function, which you can see is takes care of the barrier function value at origin, which may be non-zero. That leads to some introduction of some bias, but then for the learning of optimal control policy, this bias is removed. As you can guess, this is just a constant value. So using similar strategy where we have a zeroing control barrier function based QP, we are able to ensure the safety of the tracking, safety of exploration within the tracking problem. And using similar strategy, we are able to ensure safe learning for the tracking problem. I forgot to highlight another difference. So the value function here that we consider is necessarily taking into account a discount factor. And that is essential in order to guarantee the admissibility of the control laws learned during the process, because such a discount, such a factor, which is exponentially decaying in nature, ensures that the cost function doesn't explode, right? And so again, using some simulations, we can see how such a strategy works in the tracking case. As you can see, during the training, during exploration phase, the states may not follow the reference quite in an ideal manner. But after training, during the learning process, the performance is not bad. The difference is seen here with another state where the exploration phase itself is unsafe without the safety guarantees, but but remains safe with our strategy during the exploration as well as the tracking operational phase. So that's the tracking part. I would very much like to show you and talk to you about input to state safety. Do we have some time, Johannes? Still 5 minutes, perhaps?
Yeah, we're a little bit late, but yeah, if you just like, if you can break it down in like in 2 or 3 minutes, so I think then it should be fine. Yeah, excellent.
Great. I take the liberty because we started a
Yeah.
little bit late. So yeah,
Yeah.
okay, 2 minutes. Very quickly, the idea here, the idea of input to state safety, we have introduced very recently, where we focus upon not just the safety during exploration process, but on the quality of exploration itself. Because during exploration, it's essential, of course, to ensure safety, but it's also preferable to steer the system near safety boundaries whilst ensuring safety. So, in order to collect rich data. So, that's what we focused upon. and we propose an approach where the control policy is corrected or compensated strictly when the system is near danger or near the system safety boundaries, and everywhere else the controller remains non-conservative or relaxed. So basically, we make the QP highly conservative when the system is near these safety boundaries, and when the system is well inside, well within the safe set, the controller is non-conservative and preferably uh, negligibly conservative. That leads to collection of data which is rich, which is more informative, leads to collection of data which is typically associated with dangerous scenarios, right? And all this, and during the whole process, safety is ensured. So I'll not go into much details, but then basically we do not consider the safe set. We consider an extended safe set in sense of Aaron Ames, their work in 2017, where they proposed ISSF, input to state safety. We have adapted it within the reinforcement learning paradigm. And you are welcome to look at the work, which will appear soon. Yeah, let me just show you some simulations. So basically here, as you can see, during the exploration process, using traditional CBF-based approach, the safety during exploration is maintained, but it is highly conservative. We are, we are not collecting data everywhere. We are well within the safe set. We are safe. It's a highly conservative behavior. While using the previous approach, when we don't have any safety filter, the safety is of course violated. Using the proposed approach, we are we are much more flexible than the classical baseline, whilst being safe at all times. So here, as you can see, the exploration process takes the system to near the safety boundaries whilst maintaining safety, and that leads to rich and more informative data collection. Our work focused upon such a mechanism. Our work did not focus upon how informative the data is, but that is a perspective. Um, and yeah, what else can I talk about? So yeah, you are welcome to look at the work that will appear soon in one of the journals, right? So the conclusions are we are basically able to use CBFs inside the RL loop, not merely as an as an optimizer, but optimization routine, but that remains external to the learning process. But we are able to use it within the learning pipeline. We are able to ensure safety across the three important phases: initialization, exploration, and exploitation. And the recently proposed ISSF for RL gives us a robust framework to reason and argue about the richness of the data that is collected. I had added some perspectives, but it seems I had some problem with the recent PDF, so I'm just gonna skip that or see if it comes very quickly. So in the perspectives, we have learning of CBFs and CLFs using Gaussian process. We also want to consider environments which are slowly varying or abruptly varying. Uh, 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 Perhaps the Lipschitz based smoothness or Lipschitz constants can be used as indicators. Then how about varying dynamics? How about stochastic dynamics, where the exploration noise, the excitation noise can itself be highly stochastic and unbounded. And so these are some of the perspectives towards which we are working. So thank you for your time, and please, if you have some questions, please go ahead.
Excellent, Maya. Thank you very much for this talk. Do we have maybe one or two questions for Maya? Questions?
Okay.
We have one question for you.
Okay, great talk. It seems like I'm obliged to ask questions, and it's a very interesting talk. Thank you very much. I'm Hyosan from Kaisten Capital University. It's a touching, very delicate issue, exploration versus safety, which is like a very kind of like conflicting object. But the question was, you try to restrict the exploration and exploitation within the safe set. Under the presence of the uncertainties and so on, this may become quite conservative. But and how do you address the kind of like issues you may restrict too much if there are a lot of like uncertainties and like model mismatch and so on? That's kind of a question I have.
Thank you for the question. A very nice question. And I could not get time to talk about the ISSF condition. And this is exactly what we looked at on the ISSF work. So here we are able to, in fact, as you see during exploration process, we can consider this exploration noise. In fact, this is an additive perturbation. This is a matched uncertainty. So in fact, the strategy that we use here can be used in presence of additive or even multiplicative, matched or unmatched uncertainties. The idea would be then to consider some delta F here, delta G, or and so on and so forth, and get, write additional terms here. And then using the same strategy, we can get all those extra terms absorbed here on the RHS side. So as you can see here, this is the typical expression of CBF, which is with this additional term that takes into account all the uncertainties. That would be my solution. We did not look into it, and really it's it's a very nice perspective. I'm just looking for a student to work on that. It's a straightforward possibility. So we did not work upon that, but we instead worked upon this problem where the system is under such a noise. And as you can see, this noise is nothing but it's a perturbation or uncertainty. So I guess the same strategy, similar strategy will lead to guarantees in presence of bounded uncertainties, bounded unknown uncertainties in matched sense or unmatched sense. So that would be my idea there. And in fact, using similar framework, we would be able to guarantee the safety over an enlarged set. So here the idea would be then that during the exploration process, as we near the safety boundaries, this gap becomes the gap becomes small in the sense that we become highly conservative. So here the idea would be to make this very small as we near the safety boundaries. As this becomes very small, the denominator, this term itself will become very large, and that will lead to highly conservative behavior, very strict compensation when the system is near the safe set. On the other hand, when system is well within the safe set, such a term would be large. So this term, the whole term would be quite small, and that would lead to more sort of non-conservative behavior preferably non-conservative behavior. This is what we worked upon in the ISSF context, where we modulated the epsilon based on the value of hx. But I guess this can be applied even in the presence of uncertainties as well as during the exploration process.
Right. Thank you very much.